Now what we are going to do is, okay, now let's leave aside the ideal situation. Let's move on to practical considerations. What happens if I actually am trying to implement a filter in hardware? Okay. So right now most of our considerations are still in the domain of how do I implement something in hardware, but as you probably have sort of understood by now from the analysis that we have done, the data flow graph concept by itself doesn't necessarily restrict itself to hardware, right? If I have software implementations where each actor in the data flow graph is a function that takes a certain number of clock cycles, the same analysis that I have done so far would hold true over there as well. Okay. All right. So anyway, for now let's look at the problem of implementing a FIR filter, okay, with the equation yn equals a x of n plus b x n minus 1 plus c x n minus 2. Okay. The straightforward hardware implementation for this looks something like this. I'm going to draw block diagrams from now onwards, not the data flow graphs. They are interchangeable. I hope there is no confusion introduced in terms of how to visualize them at any given point in time. If there is any problem, please feel free to stop me and get it clarified. So the simple block diagram would look something like this. We have x of n being put through a shift register to generate x of n minus 1 and x of n minus 2. Each of those elements goes through a corresponding multiplier applied to adders, and the output y of n. Okay. As we discussed earlier, the critical path in this particular implementation corresponds to this red line that I have marked over here, right. So that the critical path length is essentially given by the time for one multiplication plus two additions. Okay. So keep in mind, when I write something of this sort, I am making certain assumptions. For example, I am ignoring things like the setup time of the individual flip flops and so on. I am also assuming that there are flip flops or registers at the very input. So x of n, in other words, is coming from a register and y of n is going into another register. Okay. Those are sort of the implicit assumptions that I am making over here that I am not really going to elaborate on. If you have a finite setup time, a finite clock to queue delay associated with the registers, then those will also add to your critical path, right. But they are just sort of, I mean, those are just implementation details, so I am going to skip those. Primarily the critical path is dominated by these factors, the multiplier time and the two adders that are in series. Okay. So for example, if I have, let us say Tm is equal to 2 nanoseconds, Ta is equal to 1 nanoseconds, these are just arbitrary numbers that I am pulling out, right. I mean, they are not real values for any given technology. It is just an example that we are using over here. The sort of one thing you can generally speaking assume safely is that a multiplication takes longer than an addition, okay, simply because it is a more complex operation, more complicated operation. But having said that, on modern processors, for example, this may not even be true, right. Both multiplications and additions are capable of being performed within a single clock cycle, and as long as your resolution, time resolution, is limited by clock cycles, it basically means that multiplication and addition are going to take the same amount of time. So again, like I said, it depends on the underlying technology. In this case, with this assumption, what we are saying is that the time period, the clock period that I use, must be greater than or equal to 4 nanoseconds, right. This is the clock period that I can use on these registers. That in turn implies that the sample period is greater than or equal to 4 nanoseconds, because in this particular implementation the sample period and the clock period are exactly the same. So the question now becomes, how do I improve upon this, right, and more importantly, are there certain things I can assume in terms of what is the best possible throughput, or how do I compute the best possible throughput for an architecture like this.